Okay, so yesterday we finished up the bits and pieces on infinite time horizon and the kind of theoretical results there. And now we're starting to talk about algorithms, okay, for Markov decision processes. So let's just quickly recap that. So these are cases where, although a lot of the examples, because we're kind of in the maths department, a lot of the examples that we'll do will be kind of solvable theoretically. Actually, if you're out in the real world, a lot of the kind of examples that you'll come across will require some sort of algorithm to solve them, and a kind of an analytically tractable solution is a luxury that often you won't be able to afford, if you see what I mean. It is useful to be able to prove things theoretically, because then you've got an idea on orders of magnitude, what things increase as other parameters increase and decrease. So it's useful to keep that in mind. But that said, often you'll need a computer or something like this to help you solve the problems that you come against. Okay, so as I mentioned yesterday, most algorithms for Markov decision processes, and these are ones where you know kind of the probabilities of the jumps, or you know, in the case of a stock or something, you know what the drift is and what the volatility is. An algorithm that goes to solve the Markov decision process will have essentially two steps. It'll have a policy improvement. Ooh, that's a rather big pen. It'll have a policy improvement step, and that is where you look at the policy that you currently have, do some sort of job to say, well, how could it do better than it currently does, and a policy evaluation step, okay, which is where you kind of look at the rewards or the value function that you're getting and try to evaluate that for the policy that you're considering, okay? Right. And just to mention references, so there's quite a nice discussion of this in this. I mentioned a book, Bartow and Sutton, that has quite a nice sort of assessment of algorithms and things like this. We'll cover some of the aspects of that book, and you can download it online. Let me have a look. Bartow, Sutton. Yeah. So we're mostly going to cover two algorithms. One's called value iteration and the other's called policy iteration. Okay, they're both treated in that text and the book by Bert Seeker, so they're kind of two main sort of basic algorithms, okay, for solving Markov decision processes over an infinite time horizon. So we started with value iteration, and I was sort of thinking yesterday, a little bit after the class, what's a good way to explain this? We'll just recall the definition here. So value iteration is an important and practical scheme for approximating the solution of an infinite time horizon Markov decision process. And essentially what you do is you start with an initial value for all the states being 0, okay? And then what you do is you look at what would happen over the next time step given that value, and you try to maximize the reward, okay? This is extremely similar. In fact, it's all basically identical to what you were doing in the exercise on Bellman-Ford, if you remember, that you looked at what was the minimum cost path from where I currently am to the end destination over a certain number of steps, okay? Right, this is very similar to something you've seen already in the Bellman-Ford, okay? Right, so what you do is you look at the maximum reward I can take over the next step plus beta times the value that I got from the previous iteration of the algorithm, okay? And that gives you a new value, right? And you just keep on plugging this in, okay? So you add the reward plus the expected value of where you end up from step S, and then update and update and update, okay? So, so I was thinking a little bit about it, that maybe like a kind of abstract definition like that doing anyone much good. So let's think about the following. That I've got, remember my robot problem. So we've got something like this. You got a reward of 1 for ending up at this square and a reward of 2 for ending here. Okay? And then we've got my robot. Okay? And he can go left or right. Okay? And so how's value iteration going to update things? So let's say this time we're going to do everything deterministically rather than random. Okay? So what value iteration will do is it will basically say everything, all the states except for maybe the end states. Let's not worry about the end states because they're not really states. They're just sort of where things end up. So the states are really these 6 squares in the middle here. Okay? And it'll start with the value of this state being 0, 0, and 0. Okay? And then what it'll do, for each state, it'll say, what can I do next? So if I'm here at this square, it'll go, if I go right, okay, I don't accumulate any reward from that move, and the value at the previous step of that reward was 0. Okay? So going right is 0 here. Or the other action is to go left. Okay? In which case I get a reward of 1. Okay? Because I end up at that state. Okay? And so at the next iteration of this algorithm, this will give me 1. Okay? And let's think about it for this state. I can go, I'm at this state, I can go right, and I get a value of 0. Okay, so 0. Or I can go left, and I get a value from the previous round of 0. Okay? So this remains 0. Okay? And by the same argument, this is 0, this is 0, this is 0. And then this one's another interesting one, where if I go left, I don't accumulate any reward from that move, and the value of the previous iteration was 0. Okay? And here, if I go right, I don't accumulate any instantaneous reward, but I get a value of 2. So we're ending up in that site where the value is 2. Okay? Right, everyone agree with that? So what's happening there is we're just evaluating the instantaneous reward plus the expected reward of where I end up at from the previous round. Okay? Does that make sense? So I'm just evaluating, for each of those 6 blocks, I just evaluated the left or right in this maximization and looked at what the reward was. Okay? Then, next round, okay, I'll be here, okay, and I can either go right or left, again. If I go right, the value is 0, okay, or if I go left, the value is 1, okay, so it stays 1. This guy, if I go left, I get a value of 1, okay, and if I go right, I get a value of 0. So you want to go left, that's going to give me a bigger number. Okay, so 1. This one, left is 0, right is 0. So 0 here, left is 0, right is 0. Here, left is 0, right is 2. Get 2. Okay? And here, well, left is 0 and right is 2, so it remains 2. Okay? Does everyone agree with that? Notice, this is the best thing I can do from this state over 1 jump. This is the best thing I can do this state over 2 jumps. I go left and left. Okay? So notice that now, if I evaluate this guy here, if I go left, I get 1, and if I go right, I go 1. So actually it doesn't matter anymore. The value is 1 for both of them. The left one here says if I go left, I get to the end and I get 1. This says if I go right, I can then go left and left and get 1. If you see what I mean. Okay? All right. Okay. There's another reason you might want to apply a discount factor. Notice that it would be better to make a jump of 1 straight away than doing a right, then left, then left. Okay, so if I had a discount factor on here, this number would be ever so slightly smaller than the left here. Anyway, okay. So keep going. This will be 1, 1, 2, 2, 2. Okay. And then it gets a little bit more interesting. This will remain left 1, right 1, left 1, right 1. And here it'll go, well, if I go left, I get 1, but if I go right, I get 2. Okay? So then it's better to go right. So this will become a 2, and a 2, and a 2. Okay? And eventually it'll go 1, 2, 2, 2, 2, and then 2, 2, 2, 2, 2, and we're done. Okay? Notice if I try to iterate again, I just end up with the same solution again. All right, so after this point, notice the next round is if I ran the algorithm 1,000 times, I just end up getting the same answer 1,000 times. Or, well, minus how many that is, 7. Okay. So that gives a basic idea of what value iteration is doing. You kind of look at the available actions, look what reward that's going to get you, and you take the better one. Okay, and that'll update the values. Okay. So essentially, you're just looking to take the value function, just keep updating it. All right, and it's basically the same idea as we were doing with Bellman Ford. You're just kind of updating the value of the distance to the endpoint in the case of like minimizing distances and things like this. Okay. Okay. All right. So that's really what that is saying. Okay. You can also begin to see why adding a discount factor might be useful, because if you apply a discount factor, it's going to discern between the lengths from the final destination point as well. Okay. And we can also do value iteration. So just to say, the two displays above, this corresponds to the policy improvement step, and this corresponds to the policy evaluation step. Okay. They're actually kind of wrapped into one thing, because if you just pay attention to what's the maximizer as well as what the maximum is, you can kind of do the two bundled together. But they are both there. All right. Okay. Also, we can do value iteration for a minimization problem, and we just replace the maximization in here with the minimization. Okay. And it's the same thing. Okay. Okay. So now we're going to prove that actually value iteration in a lot of situations converges to the optimal solution. Okay. There's more one can say. You can also talk about rates of convergence and things like this. We're not going to do that. We'll just say that it's correct that the value function is going to converge on the correct solutions. Okay. Okay. So here, for a reward function R, okay, I'm going to let L of R, so script L of R, be the new reward function taken from one iteration of that value iteration. Okay. So if R was my previous value function, this is my new value function under policy, value iteration. Okay. And what I'm going to say here is if I have a reward Rx, which is bigger than R tilde, then after I do the value iteration operation, then that inequality remains the same. Okay? So let's just show that to start with. Okay? So it preserves order, essentially, this operation here. Okay? Ooh. For some reason that jumped. Okay, so why is that? Well, if I just look at the term inside the brackets here, I'd have R of X of A plus beta E of x of a of our x hat, where x hat's the state that I reach after taking action A from state x. Okay. Well, that's going to be bigger than the same thing, but I replace this with r tilde. Okay. I'm just leaving a little space in here. Okay, why? Because that's bigger than that, and the expectation preserves order. Okay? And then I can just maximize over the sets of actions here, and this is going to remain bigger than this. Okay? So now if I maximize this over the sets of actions, and I maximize this over the sets of actions, then this is going to remain bigger than this as well. Okay? And that is equal to script L of Rx, and that is equal to script L of R tilde. Oops, sorry. Okay? So in other words, that remains bigger than that. And we can use this now to say that, show that for value iteration with positive programming, that the value function in each iteration is always increasing. Okay? So after s plus 1 iterations of value iteration, I'm going to have a bigger number than I did after s iterations. Okay? So the values are going up. So why is that? It looks like a much more difficult statement to make than this, but it isn't actually. So at time 0, what's the value of everything? Yeah, 0. And just looking back at our definition here, what is the value of everything at step 1? That's 0. So it's just the maximum of Rx of A over A. Okay? Notice that the very first step, which is bigger, V of 0x or V of 1? That one's bigger. So now, what about V of 1 of x compared to V of 2 of x? Notice from exercise 16, V of 1 is L of V of 0 of x. Okay? And V of 2 is L of V of 1 of x. That's bigger than that. So after one iteration, a value iteration, it's going to remain the same. Does everyone see that? I'll put that up a bit, sorry. So that's by exercise 16. So then, because the first term is bigger than the 0th term, the second term has to be bigger than the first term. And then the third term has to be bigger than the second term, and the fourth term has to be bigger than the third term, and so forth. Yeah? So, and so forth. That's it. Okay? basically the 0th term is less than the first term, so I apply one iteration, a value iteration, and then the order remains. Okay? So that's quite a common trick, actually, that isn't just applied in dynamic programming, but that type of trick is kind of often used for proving that different sorts of systems and dynamical systems converge. Okay, so it's a good one to know as a general trick. Okay, so that's good. That means that value iteration is somehow doing the right thing. We come up with policies and they're improving. Okay? So I'm going to skip on to discounted programming to prove that this, let's say we've got a positive program and it's discounted. It makes life easier for the proofs. We could do this for positive programming, or will in a second do this for positive programming, negative programming, but discounted is the easiest case. Okay. So I'm going to show that not only does value iteration improve the rewards, it also converges to the optimal reward. Okay? So it's one thing that you come up with better policies or better value functions. Okay? But you also want it to converge to the optimal one. Okay? Okay. So we want to show that for discounted programming that v of s of x is equal to v of x. Okay? So the answer to this is the following. That note that v of s of x is the optimal solution to a finite time Markov decision process. Okay? So why is that? So notice if I wrote down a finite time Markov decision process that lasted for s steps, okay, it got all the rewards that the normal Markov decision process over infinite time did, but then after time s the value was 0, okay, I'd have a finite time Markov decision process. Okay? And if I wanted to solve the optimal solution for that, I'd end up doing Bellman's equation, iterating backwards. Okay? That would be exactly the calculation that we did for v of s. Okay? So you should convince yourself, let's just get the exercise up. So you should convince yourself that this is exactly the same as doing Bellman's equation for a finite time Markov decision process. Okay, something that lasts s steps here with the final reward value of 0 is exactly what we're doing for value iteration. Okay, so we're actually solving a Markov decision process but over t steps. Okay, so you should convince yourself on MDP notes exercise 4 that we're doing exactly the same thing. Okay. Okay. Also, to comment from that exercise we did at the beginning, notice that we're kind of making decisions to go left or right, and we're kind of looking at what's the best thing I can do over 1 step, what's the best thing I can do over 2 steps, what's the best thing I can do over 3 steps. Okay, so from that example you can see it in action as well, that that's actually what value iteration is doing. It's saying what's my optimal policy, but over a finite number of steps. Okay, so how's that helpful? Well, we can use that to bound the value function v of s of x and say why it potentially can do better to some extent than v of x. Okay, so v here is the optimal value function. Certainly the policy that we come up with over s steps is going to be worse because it's not optimizing over all time. It's just optimizing over a finite time. So this is going to be true. Okay. On the other hand, let's suppose the hypothetical situation that you do the optimal thing over the first S time steps, and then from there on after, you just get the maximum reward you can possibly get for each time step. Okay? That would mean that I get the max reward that I can possibly get at the next time step, and the time step after, and the time step after. That would be a geometric series, okay, with discount factors beta on it. So it'd end up with a beta to the S plus 1 divided by 1 minus S. Okay? Because here I'd be getting, let me expand that out a little bit. I'll just expand that out here. So that means do optimal for the first S steps. And then I get the maximum reward at the next time step. I'd have a beta to the S here, okay? Well, I should, yeah. Okay. And then I get the maximum reward at the next time step, okay? And then I get the maximum reward at the next time step and keep on getting the maximum reward, yeah? That is going to be better than the optimal policy. Why? Because I'm doing the optimal thing for the first S steps, and then I'm getting the maximum I can possibly get in an idealized world. Okay? So it's better than any reward I could get over these time steps, so it has to be better than this. Okay? Does that make sense? People sort of see what I'm saying there? So it's sort of saying like, optimal for the first S steps, and then let's just do an upper bound on all the remaining rewards. Okay, that's going to be bigger. And if I sum that geometric series, I'm going to get this. Oh, that should be a beta, sorry. Yeah, okay. So that geometric sum is going to give me this expression here. Okay, that overall is going to be bigger than V of x. So what's going to happen to the limit of this guy as s goes to infinity? That's going to go to 0, isn't it? If I let s go to infinity, that's going to go to 0. This is going to go to the limit of vs of x. Okay, and it says the limit of vs of x is both above vx and below vx, so it has to be equal to it. Okay? Okay? And that's that. That's why, for discounted programming, why value iteration converges to the optimal solution. So it improves the solutions, but also, as we've just shown for discounted programming, it converges to the optimal solution as well. Okay? All right, so now we're just going to do it for positive programming. And you can do it for negative programming, but once you've done the positive programming case, you've basically done the negative programming case as well. Okay? Okay, so let's do this one. Oops. So we use the same idea that Vs of x is the optimal policy over s steps. Okay? So that means that this is greater than or equal to the reward I receive over s steps from state x for some policy, pi, a policy that I could in principle apply over infinite time. Okay? Now let's just take the limit on both sides. If I take the limit as s goes to infinity, Okay. This is going to go to the limit of Vs of x, and this is going to go to the reward function for that policy over all time. So the limit of this guy is bigger than the reward I can get from any policy. Okay? So then I have that limit, I can maximize this over all policies. Okay? But I can also apply exactly the same inequality I did up here, that since Vs is optimal over S time steps, rather than all time steps, and the rewards are positive, V of x is less than V of S as well. Okay, so this exact same expression holds for positive programming as well. All right? So that gives the result here also. Okay? That's that done. Okay? And the answer for negative programming is basically exactly the same idea as exercise 19 as well. Okay? I mean, the main one to do is, I think, the more important one is the discounted programming one. I think that just gets the main ideas across the quickest way possible. So if you're going to learn one of them, just learn the discounted programming one. Don't worry too much about positive programming, negative programming for this. Okay? Okay, good. Right, so basically we have an algorithm that we can use to converge for these things. Okay? And like I mentioned, it's really easy to code this up. Okay? So I'll try to get the code that I wrote up on the web. You can go online as well. There's lots of websites with people implementing things like value iteration for these kind of grid world examples. So this is quite a common example where you have some sort of robot that needs to kind of go through a maze to get to a reward at the end, and there's potential kind of places you can get stuck and things like this. And, okay. So notice here, if you did value iteration, again, we'd do something very similar to what we wrote down with the picture at the top with the first example. We'd start with all the blocks here being 0, and then it'd look, if I go left, or down, or right, which is going to give me better reward. And in this case, it'll be right, and then you kind of take the average of the instantaneous reward. And there's 2 here, okay? So what'll happen is we'll begin to sort of construct these kind of averages of the states around you, okay? As I mentioned last time, in terms of coding this up, I'll just get here. Can't remember where I put the code. So just to give you, I mean, we went through this briefly yesterday, but now we've actually gone through a little bit more of the algorithm in detail. So actually, like, the amount of stuff that you actually need to write to get the value iteration to work is very small. So most of this is just defining the model. So spend a lot of time defining what the rewards are on the grid, a lot of time, and I could probably do this more efficiently if I was better at coding, defining the dynamics of the system. Okay. Okay. But the actual update step basically just consists of these maximizations in here, these sort of 3 lines of maximizations, and applying the discount factor. Okay. So basically the guts of this piece of code is 3 small lines. Okay. So you don't need to write a lot. Okay, and then you just iterate on it. Okay, and I'll delete this clear output line for now, and we'll just run it all. So you see what it's doing. It would be better if this was over one line, but essentially notice that at the first iteration, notice it's taken the value. So this is basically, notice it's a 4 times 3 grid here. Okay. What I've done is I've started with the initial values here. This 0, 0, 0, minus 1 corresponds to the value here being 0, 0, 0, minus 1, and then 0, minus 2, 0, 0, and then the next row is this last row over here. Okay? So when I look at the kind of the output it's giving me is over the first iteration it's saying, well, with the discount factor and the probabilities of moving around, the value of this, the block that's next to the minus 1 is minus 0.18. Okay? Then the value of the next row is 0, minus 2, 0, 0.54. Okay, note this 0.54 is kind of being stuck in this position here. So it's actually beneficial to be here because I can try to move up, and if I do, the average between being at 2 or minus 1 is 0.54, it seems. Okay, that's what the computer tells me. Okay, so do that for one iteration, and that's the whole row it gives me. Okay, and then it starts with those as the new values and says, okay, now given my first row is 0, 0, minus 0.181, what's it going to give me as the new row? And notice it's evaluated now this part, and so this is actually slightly negative. Okay, so it's minus 0.0324. Okay, and then this has been made even a little bit worse, 0.2124 for the square next to the minus 1. Okay, so notice how the kind of negative number here is kind of propagating out around, and this positive number is kind of propagating out around, and this negative 2 will be kind of propagating around as well. Okay, it'll kind of start to fill up the squares until these numbers converge. Okay. So we have a whole bunch of iterations, okay? There's not that many, I've written 1,000 here, but I'm kind of massively over. I probably could have done this in about 20 iterations or something like this. This will converge to the correct value, okay? And eventually we get a set of numbers, okay? With the different values for all the different squares, and we can use those to guide us, okay? As to where we should go, okay? So the upshot will be that the right action from this square is to go up, the right action from this one is to go up, and you kind of, once these values have kind of propagated back, so this 2 has kind of propagated back over here, we'll find that, for example, if in this square, the value of going here is more negative than the value of going here, or is smaller than going right. So actually it works better to take a longer route round than the shorter, more direct route to this 2. Okay? So lots of things like, you know, like if you want to play chess and write a good program for playing chess, you kind of apply these same principles, or how to play Tetris in an optimal way, or things like this. You kind of need to look a few steps ahead as to where you're going to go. Okay, evaluate these value functions, and then make the right decision. Okay. All right. All right. A little bit. I think we'll just take a 10-minute break now, probably, and then we'll go on to